Why does L'Hopital's rule work? Well, a simple way to look at this is just to think of a limit as how they're getting to the limit point. Okay, so if we want to look at how the numerator and denominator are getting to a limit point, we want to actually see how they change or how fast they're going to go there. So this is essentially a rate of change or the derivative. And we can just then compare the derivatives of the numerator to the derivative of the denominator to see how fast they're going to the point, and we can see that ratio then would allow us to figure out where it ends up. That's kind of a simple explanation. A little bit more technical explanation and a little bit harder is if we take a look at the geometrical interpretation of L'Hopital's rule. So we are trying to figure out how f of x over g of x approaches some undefined or indeterminate point. And we want to see how it gets there. So what we can do is we can zoom into a point. So for example here, we have x squared minus pi squared over sine x. So the blue line is sine x. The red line is the quadratic x squared minus pi squared. And what we can do is we can zoom into that point. Okay, so I'm not going to zoom in too much as I can, but I'm zooming into that point. And what ends up happening is no matter how curved a function is, the more we zoom in, the more it looks straight as we zoom in. Okay, so that is called local linearization. So any curve, if you zoom in far enough, looks like a straight line. So what ends up happening? Okay, well, L'Hopital's rule is comparing f of x to g of x. And what we're saying in L'Hopital's is that the derivative of f and the derivative of g near zero is going to be the same as f to g. Well, that is true because if we take a look at the zoomed in part, if we take a look at this, if this is essentially straight, the red line is essentially straight and the blue line is essentially straight, we can just plot a slope triangle onto both of those. And when we look at that, we can compare the numerator and denominator by just the change in f, comparing it to the change in g, because the change in d is going to be the same, especially the way I've drawn this here. So notice that the change in d is shared here. Okay, that little black bit there is shared. So because that's the case, we can then say that the df compared to dg is same as f to g, and thus it kind of allows us to use the derivative instead of the f and g function. We can use a derivative as a limit, and that will give us the exact same limit of f to g.